Hello everybody. Let's start today's lecture from where we left off. I think we were talking about last time virtual memory. Okay. Do you guys hear me? Just say something. Somebody
Yes.
talked. Okay, somebody talked. Okay.
Yes.
Good. How many people do we have in our meeting? Let me see how many people we have. $58. I think that would increase. Okay. Okay. So, does anybody have any questions about the material that we covered last time? Any questions from the last week? What? You don't see my screen? Do you see my screen? Do you see my... Do you... Oh. Do you see my screen? Do you see the slides? Okay, good. So, if nobody has any questions, screen is small.
Sir, we can see your screen, but we can't see the slides. We can see your Teams application.
Let me solve that problem then. I am stopping the thing. Okay. How about now? Do you see my slides?
Yes, sir.
Yes.
Okay, then we can maybe start. Let me start from a little bit back. We said that last time. We said that. Okay, this was the important thing. Let me start from the important thing. We said that memory is a resource in operating system like CPU, and it has to be managed. To manage the CPU, we have invented processes. Now to manage the memory, we are going to invent another concept which is called address spaces. Okay, address spaces. This is what we are going to study with this chapter. It's an abstraction of memory, and with this abstraction of memory, we like to do these nice things among other things. But the most important thing is the fitting many programs to the memory. Okay, to the memory. This is one thing, because we are running many programs at the same time with the CPU. That's one thing. The second thing is protection. Okay, I like to protect my programs from the other programs. No two programs should see each other's memory, because it's their private information. These are the many things that we like to, some of the things that we like to achieve, but the most important ones. But under this topic, of fitting many programs to memory, okay, uh, even if the memory is not enough to fit all of them, I should still run my programs, okay? So I need to find some kind of a way of swapping in and out of programs. Okay, this is what we are gonna do. So the address space, when I say address space, however I implemented, should support these criteria. Okay, that's what we said at the beginning. Okay, so one simple solution was base and limit registers. With the base and limit registers, we said that we have two special registers, base register and a limit register. These are special registers like the program counter or the stack pointer. Okay, every time a program makes a reference to the memory, you add the starting address of this program to this address, and it becomes your memory reference location. Okay, and I do this for all the programs. Whenever I do a context switch, I load new memory base register and the limit register, and I save the old ones into my process table. Okay, so that's what we said. So what was the problem with the base and limit registers? What was the problem with the base and limit Because this one obviously provides protection, right? Protection is good. Protection. And the address space is good, right? I mean, when I say to the program, when I say the program that this is your address space from 0 to 16,000, and this is your address space from 0 to 16,000, it was okay. Yeah, as Ahmed said, whatever Ahmed is saying is right. He says that we cannot fit many programs at the same time into my memory if the memory is not enough. Let's say I have 8 gigabytes of memory and I have 20 programs, each one is 4 gigabytes. So it looks like I need 80 gigabytes, but all I have is 8 gigabytes, 1/10 of the whole thing. So I should find one way of doing this with my new address space concept, but it is not achievable with this kind of solution. Okay, good. So we need to find something for this one. We will come that one. Okay. So large programs do not fit into memory, and it says that it is expensive. Every memory reference is an addition, right? Every memory reference is an addition. That's fine. We are gonna do it in the hardware, and it would be fast. But again, addition, we don't like addition much. But the more important problem is this one. I cannot fit large programs into my memory. Okay, so swapping has to be done. Swapping means that you have one program in your memory. When you do a context switch and you switch to another program, you reload that program from the disk to your memory, and you write your old program to the disk so that you don't forget about it. Okay, so that's one thing, and this is one example that I gave you. Okay, so I have my program A, then I have loaded B and C. Three of them are good enough for me because I can fit them in my memory. But if I like to load another new one, D, there is no space, so I need to find space. There is no space enough. So what I do is I write my process A to the disk, and now the space is available. I load D, and then then I need to switch back to A. What do I do? Even though I have good enough, large enough space for A, okay, I cannot fit it in there because the memory is fragmented. The memory is fragmented. Fragmentation is an important problem with this kind of swapping. Also, to solve the fragmentation, maybe I can move B down there, C down there, and there would be enough space for A, but that would take time. That's called compaction. Fragmentation is a bad thing. Compaction is something that we use to solve fragmentation, but this one is expensive because it needs CPU time. It's inefficient. But if this is our solution, then we have to do compaction from time to time, taking care of the memory from time to time. Okay, so this is what we did last time, swapping. And we said that maybe we should maybe we should allocate more space than the process needs for now, because I know that the stack will grow, heap will grow, and I will need extra space. That means that our process sizes will be larger than they look at the beginning. That's another problem, but we have to handle it. Okay. So before we find a solution, to this swapping program, okay. Another problem with this approach is, let's say this is my memory. My memory is like 32 kilobytes large, but I have a program that needs 48 kilobytes. So in this case, I cannot fit my program into memory. You might say that your computer is not good enough. Buy larger memory, more memory, and you will be fine. That might be a solution, yes. But I mean, in some cases, buying extra memory just for one program is too expensive. Okay. And I know that if I write a program, I know that I don't need all the data at the same time. I will need part of the program, either whether it is data section or the instruction sections, and I don't need all the instructions and I don't need all the data at the same time. The program will run in sequence, okay? Some part of the programs are not used at all, right, at the beginning. Some part of the programs are not used at all when the program runs in a regular way. So maybe I should take advantage of the situation. So this solution, swapping in and out, doesn't solve this problem. Also, it has this fragmentation and problem and compaction expense. Okay, so Ahmed, okay, so that was the last. Okay, that was his last answer. So it's a new question. Okay, good. So let's go back and let's look at this problem of memory management. We said that this is my memory, and some part of the programs will be using this part. Let's say this part is empty, nobody's using it. This is B, this is C, this is OS. How do I keep this information? For this one, we had two solutions. One is a bitmap solution, and the other one is a linked list solution. Bitmap solution says that I will divide your memory into, let's say 4 kilobyte pieces, and I will keep a bitmap like this one. Each one is a bit. This one corresponds to this page. This one corresponds to this page. This one corresponds to this page. And this one corresponds to this page. Okay. So this is my bitmap table. And if the memory is occupied, and I will say it is 1. If the memory is not occupied, it is 0. So this is the bitmap representation. An alternative is linked list representation. Okay, linked list representation. Linked list representation says that I will keep the parts of the program, I will keep the parts of the program that belongs to a process like this, a node. It says that I will start from page 0 and 5 pages. 1, 2, 3, 4, 5. Okay, this is occupied. And I have a whole, okay, starting at 5. This is 5, right? And total of 3. And I will have a process at starting from 8. It is 6, 1, 2, 3, 4, 5. It goes that way, okay? So the size for the bitmap is always fixed. Let's say I have 1 gigabyte of memory, okay? 1 gigabyte of memory. This is 1 gigabyte. Okay, it looks like it's 16, but it is gigabytes. Okay, 1 gigabyte of memory, and let's say these are 4 kilobytes. 4 kilobytes means that it is 2 to the power 12, right? Yeah, 12. So each one is 2 to the power 12 bytes. That means that I need, how many bits I need? I need, okay, this is my memory. If I divide this by 2 to the power 12, that means 2 to the power 18. Okay, 2 to the power 18, that means what is 2 to the power 18? It is 256, right? 256 kilobits, right? This is kilobits, not kilobytes. If I like to convert this to kilobytes, I need to divide this by 2 over 3, and it is 2 to the 15. Okay, so it is still very large. 2 to the 15 is divide 256 by 8. It is it is 2 to the 15, right? 2 to the 15. It's a very large amount of space that I need to keep track of all the time. But this one says that if the whole memory is available, then I will need only one node, whole node. If I have only 1, 2, 3, 4, 5 processes in my memory, this is what I need. Okay, so that's the advantage and disadvantage. This is fixed size. This is a linked list. I always need to traverse this one by one. This one is directly accessible, etc. Okay, good. Any questions about linked list and the bitmap representations? So the the thing is, whenever a new process starts, I need to find place in my memory so that I can fit in my new process. Okay, I need to find the process. Let's say I have a program. Let's say, okay, question for you. Any program F will be loaded. It says that it needs 2 pages. Okay, which one would you give to this one? This one or this one or this one? Question: which one would you give to, which one would you assign, at what place would you put this process A in my memory? This position, or this position, or this position, or this position? Which one? Ahmet says that second one, and the other people, they don't say anything. When you look at the whole picture, second one would look like nice, but I think Ahmed says that it is second one because Hussein says the same thing too. Mustafa, what do you mean video is not in sync? I mean, do you see this page, right? There are 1, 2, 3 empty slides. Okay. So the idea is if you choose the second one, okay, if you choose the second one, that would look nice, but you need to make a search for a second one. So it's kind of expensive to find the best fit example because, okay, if you fit F to here, F will be here, okay, F will be here, and there is no fragmentation problem, but to be able to find this position, you need to make a search in the bitmap or in the linked list. Okay. What do you understand, Mustafa? The question is simple. There are 3 spots, and which one would you choose? That's the question. I have been talking on this slide for the last 10 minutes. I am not out of sync for 10 minutes. The question is, I have 3 spots available. Which one would you choose? Okay, so the Ahmet Yasir says that maybe we can also hold a list of holes and their capacity on the side. That's what I have, right? This and hole, and hole. You are saying that let's have another linked list that is a whole linked list still, but you need to make a search in that, right? So you need to make a search. So the idea of using the idea of using the best fit position is good, but that's kind of expensive than, let's say, first fit. And we're going to look at them one by one. Okay, so the memory management with bitmaps, that's what we said. So the size of the allocation unit is a design issue. That is the page size. Should it be 4 kilobytes? Should it be 10 kilobytes? 1 megabytes? Doesn't matter. It's a design issue, and searching for K allocation units is expensive. You need to make a search in there because sometimes you need to check all the bits one by one. Okay, is this available? Is this available, etc. With the linked list, if the memory is sparse, it is not used much, then maybe this is faster. But this one, most of the time you will be making lots of search. This one, it might be a little bit more efficient than we're gonna see it. Okay, so let's look at this memory management with linked list again. With the linked list, I mean, it doesn't matter what you do with this bitmaps because you need to make a search all the time, and you need to make almost all the time half of the bitmaps. But this one, if you are smart, maybe you can do a little bit better. So what do I mean? And we will see. Let's say this is our structure. Okay, I have 3 processes, A, B, and A, X, and B. X will be terminated. When I terminate X, my linked list structure becomes like this. In this case, B, when I terminate X, okay, I need to make this merge. You cannot do this. You cannot, let's say, I have a process, and then I have a hole, and then I have another hole. You cannot say that. You need to merge, okay? You need to merge these two. Okay? You need to merge these two. So this is what happens with B. I what I do is with B, what I do is after I terminate X, I merge these two, and these two become a single whole. And the same thing is again, when I do this, I need to merge these two, and if I terminate this one, merging happens like that. So that means that after you delete something, you terminate something, you need to go back to this list and make sure that consecutive holes are merged. So how do you sort this linked list if I am going to merge the available space like this? So how do you sort your linked list then? Question: how do you keep your linked list sorted if you are going to do this kind of merging? Which one would be better? Would you sort it with respect to the size of the holes, or would you sort them with respect to the some other property? How? Mustafa, you understand the question? You don't need any synchronization for this one. I ask the question. Selman says that memory address, that's right. If I sort this linked list with respect to the memory address, this is address 0, 5, 8, 14, 18, 20. Okay, so this is sorted with respect to the memory address. So if I terminate this process, if this becomes H, right? Let's say if this becomes H, then these three will be merged and they will be like this. Okay, here I will say this is a whole, and it will start at 18, and 2 plus 6 plus 3 is 11. And then, oh, no. Sorry. It is 18, and it is 2 plus 6 will be, okay, it is 2 plus 6 will be 8, and it will be like that. Okay, so these two will be merged together. Okay, good. So memory address is the right way if this is your concern, but there are other things that you need to worry about. So let's look at some examples, memory management algorithms to find the available space. Also, we need to worry about how we make the merging after the terminations. The first example is first fit. First fit says that okay, this is my memory configuration at the beginning. First fit says that, okay, scan the nodes from the beginning, and find the first available spot. Remember F, it needed 2 pages, okay? I will say this is a process. There is a hole. It is if F needs 2 pages, but this one has 3, so I will fit F here. Okay. So and this part will be fragmented. This part will be again. This part will be free. I am keeping my finger on this empty part so that Mustafa can see it. This part will be empty, but it will be only 1 kilobyte, right? Or maybe 4 kilobyte empty place. It will be fragmented, and it will be very difficult to use this one later because no process is small enough to fit in this place. Okay, so this is first fit. First fit. It is very simple. It doesn't do lots of search. It just finds the first available place and it allocates that part, but it causes some fragmentation. Okay, so the first fit causes some fragmentation. Traverse the list until a large enough block is found. Allocate as much of it as needed. Return rest to the free list. Okay. When freeing memory, okay, you must merge the adjacent blocks, and that's fine. Okay. So if you use first fit with the next fit heuristic or the policy, this is what you do. Okay, you're gonna do next fit. Last time I used this spot. Okay. In my next memory search procedure, I will not start from the beginning. Okay, I will not start from the beginning, but I will start from this position. Remember, this became okay. Let's draw this one. This one went away, and I have F5 2, and then whole 7 1, and then this. So my pointer will be at this position. Next fit says that I will start my next search from where I left off. Okay, this is next fit. Okay, so next fit is used with the first fit. First fit always start with the beginning of the list. Next fit start with wherever I left. Okay, this is next fit. So whatever you suggested before was best fit. You said that, I think two of you said that, second one, that's the Mustafa's synchronization problem. Hüseyin Sabri and Ahmet and two more people said that second one, they were using best fit. For the best fit, you need to make a good search. Okay, search the whole list, find the best suitable situation. If you find the perfect fit, then use it, but most of the time you will not find the perfect fit. Okay, so you will have to make a search. To find the best fit. Usually you'll have to traverse all the linked list. Okay, so we have a question. Kamil says that when we try to allocate, for example, 14 kilobytes for a program, we try to find consecutive holes and we concatenate them until we get bigger. Well, yeah, Kamil says that, do we do compaction, memory compaction, to get large enough space for our new program? You may have to. Okay, you may have to, but with this simple techniques, we will not talk about compaction yet because we have a very nice solution for the compaction with the virtual memory. So I mean, 14 kilobytes, I don't have any 14 kilobytes of space in this configuration. All I have is 3 and 2 and 3, right? So I don't have it. Maybe I need to make a compaction first, but as I said, I am not dealing with the compaction algorithms yet. Okay, let's go back and go to best fit. Okay, first fit seems wasteful. There may be an exact match further down the list, so solution is best fit. Let's look for the best fit. As I said, perfect fit will rarely be available. Perfect fit is rare. You will not find perfect fit. So best fit will be you will find a memory position that is slightly larger than your needed space. Okay. Okay. That means that if you find slightly larger than the required memory, means that you are gonna cause more fragmentation, right? So best fit isn't more efficient because it causes more fragmentation, more wasted memory, unusable memory. So you need more fragmentation. So it looks like best fit is not much better than first fit or the next fit algorithms because it causes fragmentation. It causes fragmentation. By the way, for the best fit, maybe if I order my linked list by size instead of by memory position, then doing best fit would be more efficient because you would scan your linked list starting from smallest to the largest. As soon as you find the available memory, large enough memory, then you stop. You don't have to scan all the thing. Okay. So if you order linked list by size, that would be better for the best fit. But there is a problem with this one. Well, searching for the memory would be efficient, but something else would be inefficient in terms of CPU time. What is it? Searching would be efficient, but something else is not efficient. Any answers? Anybody? Just turn on your microphone and talk. You understand the question? With the best fit, if you order your linked list by size, making a search would be a little bit more efficient because you don't have to scan the whole list. As soon as how do you make a search in if it is the size? Let's say this is my whole. It starts at address 10. It is too long, and then it is a whole at address 2, and it is 3 long, and another whole address, let's say 11, 13, and it is 5 long, etc. So when you scan this picture from beginning to the end, as soon as you find the large enough space, you stop. That is efficient. But that makes something inefficient. It says that possibly to always using the same memory areas. So what is wrong with using the same memory areas all the time, it is? I don't see anything wrong with that. Yeah, Selman says that you can't merge if it is not sorted by address. Merging after termination would be more difficult. Of course, you could merge it, but you need to spend more time. Previously, merging would be efficient because the whole list or the linked list would be sorted by the memory address. So merging would be more difficult for this algorithm if you order the linked list by size. Okay, good. So let's move on. So people say that let's if best fit did not work, let's use worst fit. The idea is this: let's lower this fragmentation thing. Okay, what is worst fit? Find the memory position. Let's go back to our original linked list. Okay, this is our original linked list again. The question is the same question. We are gonna use the worst fit. Which one would you choose for the worst fit? Okay, this is best fit. It is either this one or that one. Why? Because of course, my program fits in on all of them, okay? But these are the worst fit results. Why? Because they are much larger than what I need. So idea with the worst fit is, okay, let's address this fragmentation issue. Okay, pick the largest block and subdivide it. So always you use your largest block. So to find the largest block is not a big thing because I keep a pointer to the largest block, and it is available there, and I just divide it into two parts. One part I am going to use, the other part will not be used. So that's why I am not causing much fragmentation. Okay, that's the idea, but it turns out that it is not that good. Best fit and the first fit are better than, and they are actually the first fit and best fit, their performance in terms of fragmentation is similar. Okay, so how they make these experiments? They make this simulation. So like your homework, okay, they implement a simulation environment. They implement all of their uh, memory allocation, memory management algorithms on there, and they measure the fragmentation. Okay, they find they measure the amount of need for the compaction. Okay, for the first fit, they say that almost 1/3 of the memory may be unusable. That means that it is all fragmented. Okay, so people had to find lots of other ways of doing the memory organization. Okay, so we just looked at a few of them. We just looked at worst fit, best fit, first fit, and the next fit. Okay, good. So some people say that. Okay, keep two linked lists. One is the occupied list. Occupied list says that I have a process starting from address 07. Okay, then I have another process starts from 10 and its size is 11. Then I have another one that starts at 20 or maybe 30 and 5. And there is a holes list. Okay, there is a holes list. In the holes list, okay, I have a starting address of 5 and it is 2, and let's say I have a hole at 20 and 2, etc. If you keep your occupied and the whole list, maybe you can use your available memory, empty memory, to keep your whole list. Okay, what did we say? Let's say this is our operating system. Process A, empty space. Process B, again empty space. Use one of these empty spaces to keep your whole list. Okay, because nobody's using them, so you can use them to keep your whole list. Nice thing is that if there is no available space, then you don't need the whole list then, right? So that's one idea where you could be more efficient. Good. Any questions so far? Any questions? Okay, so people, this is a question. He says that wouldn't keeping two lists be inefficient because when we make a change in memory, we need to update? Yeah, that's true, but you are gaining some memory space. So there is a trade-off between using the CPU time, the memory, okay? By spending more CPU time, you are gaining some memory. That's the idea. Okay. So Kamil, it depends on your algorithm. Okay. Do we have to keep the whole list in descending order of size or memory position? It depends on your. Um, implementation. If you are doing the best fit, right? If you are doing the best fit, remember for the best fit, making a search is good if you keep them by size. But for the first fit, it is the memory. So it depends on your. It depends on your algorithm, memory management algorithm. Okay, good. Okay. So still we did not solve this problem of if I have many programs and I like to fit them in my memory, I cannot fit them. Okay. Let's say, as I said before, I have program C that is larger than the whole memory. How am I gonna fit them? Some people came up with this idea in 1960s, overlays. Okay, they say that as a programmer, they say that this is my program. Let me use my let me use my blue pen. This is my program. Let's say my program. Okay, this part of the program, let's say O1, I will use this part at the beginning of the program, and I will use this part at the middle of the program. During the program execution, I will use O3 and O4. And in them, of course, this is my instructions and data. Instructions and data. Instructions and data, etc. Okay, so I divided my program into 4 large sections, overlays. They are called overlays. And I tell the operating system that this part will be in the memory at the beginning. Then you should load this part, then this part, and this part. And I don't need all of them in the memory all the time. Okay, these are called overlays. These are all the overlays, and the programmer split the programs into little pieces and tells the operating system that I need to load now O2, I don't need O1. I need to load O3, I don't need O2, etc. Okay, so this kind of solves the problem, right? I mean, if I have this large program C that will not fit into my available memory, so I will use this overlay idea. Okay. So what would be the problem with overlays? What do you see as the overlay problem? What do you see as the problem for the overlays? That was a nice idea in the 1960s. As always, like everybody, everything else, it is hard to maintain. Just explain it a little bit slow. Yeah, Yusuf, it has to be slow, but there is no other way around it. I mean, writing something to disk and loading them back is slow. Yeah, that's true. But I mean, Ahmet Yazir says it is hard to maintain. Yeah, I mean, for the programmer, it's a difficult task. I mean, the programmer has to manage part of the memory, has to do part of the memory management by himself. And that's a task that is not easy. Okay, and when they make an error, when they make an error, that causes lots of problems you wouldn't understand. So leaving this task to the programmer is not a good idea. Okay, okay, so it requires special skills for the programmers. That's why, although the idea was nice, they abandoned it, but they say that why don't we do this overlaying with the operating system? Operating system does the overlays. So they invented virtual memory. Okay. With the virtual memory, all the problems of allocation inefficiency, that is the first fit, etc., compaction, relocation, memory protection, fragmentation, etc., they are all addressed. Okay, they are all gone. Okay, so instead of using the methods that we have introduced to you a few minutes ago, we will use virtual memory. And virtual memory, before taking break, let me show you the virtual memory. Virtual memory does this. Okay, whenever the CPU says that I need to access a memory location, there is this memory management unit. It translates that memory address to the physical memory address. Okay, CPU always thinks that it is addressing some memory, but in reality it is a virtual memory, and this is how virtual memory works. Let's say this is our physical memory. Physical memory is 32 kilobytes long. Okay, 32 kilobytes long, and I divide my physical memory into small pages. Each page is, in this case, 4 kilobytes long. Okay, each page is 4 kilobytes long. So I could fit 32 over 4, 1, 2, 3, 4, 5, 6, 7, 8 pages in my memory. In my memory, there would be at most 8 pages. Could be at most 8 pages. Let's say I have a program that needs 64 kilobytes. Well, in this case, I will make this into a few overlays, or the virtual memory says that, okay, you will divide your 64 kilobytes of virtual memory into 16 pages, okay, virtual pages, and I will use this mapping. If you access a byte in this first virtual page, your physical address will be in this page. If you access anything in this first one, you will be here. In the third one, you will be there. In the fourth one, you will be there, etc. See these X's? If you like to access this memory location, it is not in the memory, so it has to be read from the disk and read into the memory. So this one, they are not in the memory, they are on the disk. So the program usually, it says that the program, I need to load a value from this position to my register A. Okay, the programs thinks that they have 64 kilobytes of memory, but in fact my memory is paged, and each page is mapped to my physical memory. Okay, so if I do it, it's like overlays, right? Automatic overlays. My program doesn't know anything about overlays with the pages. My program works as usual. It thinks that it has its own CPU and its own address space, virtual memory, but the address translation in this case is done automatically by this memory management unit. This is very similar to, it is very similar to what we did with the base and limit registers. Remember, with the base and limit registers, every memory reference is an addition. This one, every memory reference is a mapping from this virtual page to the physical addresses. Okay, so this is the idea of virtual pages, virtual memory, and we will see the details of this after the break. Okay, let's take 10 minutes of break now. Okay, let's continue with our discussion about paging and virtual memory. And do you guys hear me? Are we ready? Can we start?
Yes, yes,
Okay, good. So as I said before, virtual memory is kind of answer to almost all the problems that we have faced so far. It says that address space is there. Yeah, well, I mean, from the beginning, we always wanted to have an address space that is an addressable address private for each process. But our address space is broken into chunks called pages. Our address space is divided into pages, and the CPU always sends addresses in virtual memory. CPU thinks that it has 64 kilobytes of data. This is what CPU thinks, or the processors think. Okay, but in fact, I have, let's say, 32 kilobytes of data, 32 kilobytes of physical memory. This is my physical memory. So whenever I do a memory addressing, the memory management unit inside my CPU or on my system has to translate my addresses from this virtual address space to physical address space. Okay, and this mapping is done by the pages, and it is done in a very efficient way. It is more efficient than the base and limit register adding operation. Okay, and the programs, they don't need to be contiguous areas on the physical memory. That's the best solution. See this case, my program is addressable from 0k to 0 to 64k's. Okay, and my process thinks that it is addressing a contiguous memory space, but in fact in the physical memory my memory is not contiguous. My zero, the first page is at this location, first one is at this location, third one is at this location, fourth one is at this location. So it keeps changing the positions all the time. So it doesn't have to be contiguous. That means that finding the best position, memory fit, best fit, worst fit is no question at all. I don't need to place all of my program into the same contiguous area. I divide my program into 4 kilobyte pages, and I do my allocation and deallocation with the 4 kilobyte sizes, and I don't have to make any search because any place is good enough for me. Any place is good enough for me. That's another advantage. That's another advantage. So as I said, it eliminates all the problems of allocation efficiency. I don't need to make a search for the best fit, worst fit, etc. Merging of pages is not a question because I don't do any merging. Okay, I don't do any merging. I don't need to do any compaction. Fragmentation is not a problem. At least external fragmentation is not a problem, and we are gonna see what it means. Okay, I don't have to do any relocation, no compaction. Okay, and memory protection is automatically solved, and we're gonna see that. Okay, as I said before, the CPU sends, okay, 64 kilobyte assuming addresses, but these addresses, let's say 64 kilobytes, right? 64 kilobytes. So for the 64 kilobytes, how many bits do I need for the 64 kilobytes? It is 16 bits, right? 16 bits. Is that true? 64 kilobytes, 16 bits. But my memory is 32 kilobytes. So it is 11 bit addresses. Okay? Somebody's trying to say something? No. Okay. So that means that when I. No, this is not correct. This is 15, sorry. Not 11, but 15 bit. Okay. Okay. So I need to translate the 16-bit to 15-bit, and this translation is done by the memory management unit. It is done automatically for every memory reference, and it is done in a very efficient way. Okay, in a very efficient way. So let's look at how it is done. This is the picture that I showed you before. The relation between the this is virtual address space. Let me give you some uh, terminology. Okay, this is my virtual address. This is my physical address. Okay, this is how much RAM I have on my memory. This is what each of my processes think that they have. This is virtual. Okay, this part is virtual address space. This part is physical address space. Okay, and each page on my virtual address space is a virtual page. Okay, size of the virtual pages is your design decision. For this case, it is 4 kilobyte. Okay, so these are virtual pages. Each of these boxes in the virtual address space is virtual pages, and each box in the physical memory address, are called page frames. Page frames. This is virtual page. These are the page frames. Okay. So the text from the book, it says that every page begins on a multiple of 496 bytes and ends with 495 addresses higher. So 4K to 8K really means between these two numbers, and 8K to 12K is this, right? Because we are doing addressing in terms of 2 to the power something. So let's look at how this translation is done. In a very efficient manner. I mean, of course, let's say I have an array, let's say an integer array, virtual array of size 64, 536. Okay, and at each position of this array, I place this. Let's say if you like to access the zeroth address, it will be at position, let's say, where is 0. It is 8192. Okay, 8192. V1 is 8193. V2 is 8194, etc. And I can fill this table like this, and this mapping could be done with this array. Okay, what would be the problem with this approach? And I have a very large array of size 64 64Ks of array, and for each element I indicate this mapping, okay, from this virtual address space to the physical address space. By the way, some of them would be, let's say, v 10,007, something like that. It will be, for example, -1, so that it knows that it is not available in the memory. So what would be the problem with this approach? So to do this address mapping with the memory management unit, okay, I need to make this mapping, okay, and I keep this array, and this array will do the mapping. So what would be the problem with this mapping? Turn on your microphone and talk.
Mapping virtual addresses to physical addresses would cost.
Ahmet, say it louder. I couldn't hear you.
Mapping from virtual addresses to physical addresses is expensive.
Why? It is just simple memory lookup. Why is it expensive? I just look at this number and I get this new address and that's it.
But we are doing it many times.
Well, I have to do this anyway, and I will have to do this mapping anyway because all the addresses has to be translated that way. I mean, I have to do this every time I make a new memory reference. That was the case with our base and limit registers too. So the time requirement, time penalty will be there. But this circuitry is large enough to handle that one. Is this circuitry is fast enough to handle this one.
Can I ask something?
Sure.
Uh, uh, is is the array of virtual address on the memory or on the where is it actually?
It is in the memory management unit because this translation will be done by the memory management unit. So the memory management unit, CPU says that load to my A register this address 5711. Okay, so it sends this information to the memory management unit. Memory management unit says that okay, I have a virtual address table. I will get this number and this is your physical address. Use this physical address. So it will send this physical address to the bus and the memory will give me this address. So what's your comment on this?
Will it take much space or
Exactly.
how hard will it
Exactly.
be?
I mean, remember what was the size of our memory is our physical memory is 32 kilobytes, right? And 32 kilobytes is all I have. And I am trying to address this with the 64 kilobyte of virtual memory. And for that one, I need this kind of an array. This kind size of this array is larger than my physical memory. This is not a good solution. It is practical, it is fast enough, but this is too large. I cannot keep this kind of data in my memory management unit because my memory management unit size cannot be larger than my physical memory. Because memory management unit is part of the CPU. It has some registers, but it doesn't have that many registers. Okay? So the idea is this. Idea is some kind of an address translation like this one, but it has to be done much more efficiently, more efficient in terms of memory usage than this. Okay? Everybody understand this? So let's do this. Let's do this without needing 64 kilobytes of or the 64 kilo addresses of memory management unit positions, registers. Okay, so this is how it is done. So let's say I need this address. Okay, I need this address. This address is 8196. Okay, and it has how many bits in there? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 and 16 bits. Okay, so it is assuming that I have 64 kilobytes of data. So it looks like Ilhan assigned you the attendance, right? Okay, so fill in your assignment. Ilhan, how many minutes do they have? Let's give them 10 minutes. Okay. So, but this is my memory management unit, this part. Let me put it in green box. This is my memory management unit. My memory management unit will take these 16 bits, okay? It will translate into a 15-bit address space, okay? So as you see, there are 15 bits here, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So this is 15 bits. Okay, so it is addressable memory of 32 Ks. Okay, how do we do this translation? How do we do this translation? It says that, okay, it says that your most significant 4 bits, I will take these 4 bits, okay, this will be your page number, virtual page number. Your virtual page number is 2, because if you get this, okay, this is 2, okay. I will make a lookup using this value in my page table. There is a table called page table. It says that for your first table, for your 0th entry, your entry is this, and second and third. There are a total of 16 elements in them. Because in this picture, I have 16 virtual pages. See, I have 16 virtual pages. For each page, there is an entry. For each page, there is an entry. Let's wait for this to. Doesn't work. It keeps them in the cache. No, I think I need to restart this. So for each page there is an entry, and that entry tells me the physical frame number, page frame number. Okay. All I do is I do a very simple lookup. Okay. When I do that lookup, I don't make a lookup on the whole address, but I make a lookup on the very simple. What is this? Did I load the wrong program? No, I loaded this one. Okay. Good. Yeah. So when I make this lookup, I say that I will get this 4 bits, only 4 bits. 4 bits can represent a number from 0 to 15, right? So the size of this table will be only 16. So I make a lookup, okay? Let's say it is, I am making this lookup from 8,196 address, okay? I get the 4 most significant bits, okay? This is number 2. I get here and it says that your physical page frame number is 110. That means it is 110 means it is 6, right? 6. So you will get the number 6, but I am using binary, and I will put the 6 in this address. So this address is same as this address. Okay. My physical address at the top is the same as my virtual address at the bottom. Okay, at the bottom my virtual address, my physical address. The part that I mark with green is the same as the part that I marked with green at the top. It did not change at all. So this green arrow is transferred directly without any modification. All I modify is this blue part. This part is modified with this one. So the idea wise, it is the same idea that I have used here. I made a lookup table of size 64 kilo words. Okay, that was my solution. That was bad because it needed so large space. But here, what I'm saying is, don't make this kind of large lookup. Your lookup will be only on the most significant 4 bits. So you put these 4 bits into this array and you get 3 bits back. Okay, so this is a mapping. So this part of the green part is the same, blue part changes. So this way I translated my 64 kilobytes of virtual address into my physical address. Okay, so I made a lookup on my virtual page addresses and converted them to physical frame addresses. Okay, so this part is called offset. This part is called offset, and this part is called virtual page number. Okay, virtual page number. So that's the whole idea. The idea is the same as what I introduced you before, but that one needed a very large memory space. This one doesn't need that much. Okay, any questions so far? So Kamil has a question. What if virtual address refers to somewhere that is not located in the RAM? That's a very good question. Let's say this one, instead of pointing to here, it points to this position, right? That's what Kamil says. When I look at that position, it looks like, that position is marked with a 0. That is, this part is present absent bit. Okay? What do I mean by present absent bit? It says that this page is not present in the memory. So it is not in the memory, then it has to be loaded from the disk then. So this situation is like this situation. If I need to access something at this position in my virtual memory, it is not in the memory, so it has to be loaded from the memory, from the disk to the memory. So for that one, I need to run, that's called a page fault. Page fault means that the page that I need is not in the memory. It has to be loaded from the physical disk to the physical memory. That's the page fault. But as you see, there is no space available here. So I need to maybe write one of the physical pages to the disk and make it available. So what I'm going to do is, maybe this one, number 3, I will make it X, and now this one will point to it. Okay, this is called page replacement. Page replacement. Okay, page replacement means that I need a new page from the disk on my memory. That page is not available, but in my memory there is no page available either. So I need to write a page from my memory to the disk. So which page should I kick out from my memory is a decision, and for that one I need to run my page replacement algorithms, and we are going to look at those algorithms in a careful way in this chapter. There are many page replacement algorithms. Okay, remember, for our previous memory configuration management, we have the when we make a search for the available memory, worst fit, best fit, etc. With the virtual memories, okay, virtual memories, we don't have that kind of search problems, but we have problems for the page replacement. Which page should I replace if I need to? Okay, Kamil? So again, if I out of my mapping, if I reach to this position, it says that this location is not available in my memory, present absent bit, then I need to run my page replacement algorithms. Okay, any other questions? So this is very simple actually. All you need to do is, okay, this is how many bits are there? There are 12 bits in this green part. 12 bits. 12 bits means that 4 kilobytes, right? So actually this is an address, this green part is an address in my virtual page. Remember, my virtual pages are in 4 kilobytes, okay? They are 4 kilobytes each. So this one is good enough to make an address inside a page, inside a virtual page. This one determines the virtual page number, but this is a virtual page number. For the physical memory, I need the physical page frame number, and this is my physical page frame number. All I need to do is replace this number, this 4 bits, with this 3 bits, okay, and put it at the top of the beginning of the physical address. Do that replacement. This is faster than addition. Remember, for the base and limit registers, the problem was addition was slow. This one is much faster than addition, because for the addition we have this carry problem, bit carry, right? You need to start from the least significant bit and do this addition in a sequence. This one is a one-shot algorithm. You just replace this one with this one. That's it. And how do I keep, I mean, is this large enough to fit in my so question, where does this table live? Where is this table located, page table? Where is this page table located? Maybe just to help you, let me, yeah, exactly, MMU. It is located in my memory management unit here. It is part of the CPU. So what is the size of that page table? It is just 16. It is not 64Ks, okay? It is not 64,000. It is just simply 16. So only 16 registers are good enough for me. 16 registers are good enough for me. So with the memory management unit, I make a lookup in my memory management unit table, page table, and this page table is good enough for me to make this virtual to physical address translation. And some of the context switch time comes from saving this page table and loading this page table, because each process has its own page table. Look at this picture again. This is a virtual address space for a process, for a single process, okay? And this page table is different. This page table is different for each process. So when I do a context switch, this page table has to be saved and new one has to be loaded. That's one of the most expensive things of making a context switch. Okay, remember, with the context switch you have to save all the registers, and these are the page tables are the registers that you need to save and load. Of course, the most expensive part comes from the cache hit. You need to invalidate your level 1, level 2 caches and etc. That would be most expensive. Still, this is part of the context switch time, saving and loading the page tables. Okay, let's look at these definitions. I think I talked about them. Each program, each process, each program has its own address space, which is broken up into the chunks called pages. So this is my process. My process has 16 virtual pages, okay, my pages. The program generated addresses are called virtual addresses. So these are my virtual address space, and each time I need the address position in this memory position, I am producing a virtual address number, okay, virtual address from the virtual address space, okay. The virtual address spaces consist of fixed size unit called pages, and the corresponding units in the physical memory are called page frames. Okay, these are page frames on the right. Mustafa, I am keeping my finger for a longer time for the synchronization problem. On the right side, each one is called a page frame. On the left side, each one is called a virtual page. And memory management unit does this translation from the virtual address space to the physical address space. Okay, any questions? So it looks like this is good. Okay, let's look at the actual implementation. Actually, this is the implementation. Any virtual address is divided into two parts. One part is the offset part. Okay, this is the offset part. This is just 12 bits for our case. This is the green part, and this is just 4 bits. 12 bits and 4 bits. Okay, so total of 16 bits of virtual address. 16 bits means 64 kilobytes of addressable space. So what am I gonna do is I will keep the offset part exactly the same. I need to replace this V with a 3-bit page frame number. Okay, so I take this V, put this into this page table, get the 3-bit part out, and do this. Okay, so my virtual address of 16 bits becomes like again, this is 12 bits, and this is now 3 bits. Okay, this is 3 bits. So this is a total of 32 kilobytes of addressable space. So your lookup is done using this array, just a simple array. You put V, okay, you put V, maybe blue, into this position, and you get your 3 bits out, and you concatenate this 3 bits with this 12 bits, so it is 15 bits of address. That is at most 32 kilobytes. This is as simple as this is very simple. This is what the memory management unit does. It takes these 4 bits out of this the most significant 4 bits. Okay. 4 means that there are 2 to the power 4 of virtual pages. 3 means that there are 2 to the 3 pages of physical frames. So there are 8 physical frames and 16 virtual pages. Okay, Kamil has another question. Is there any phenomenon caching the virtual table in order to... Well, virtual table, actually, I mean, that's a good question, but this table is already in the memory management unit, and memory management unit is part of the CPU. This is already fast enough. Yeah, that's a good idea, but this is already fast enough. Each one is a register, actually. I mean, this one is a register set. This M is a register set. Okay, so there are 16 special registers. They are used for this address translation. It is already fast. You cannot get any faster than register access. Okay, register access is very fast. But we will come to that idea because this is too simplistic. I mean, a 64 kilobyte computer and 64 kilobyte computer and 32 kilobyte of physical memory nowadays is kind of, it's like, it's not even a toy, right? It's just, Very simple machines. Nowadays, our address space is 48 bits. So I can on my i5 computer, my programs can address this much of data. How large is this? Okay, 10, 20, 30, 40, 50 kilobytes, megabyte, gigabyte, terabyte, right? And after the terabyte, I have petabyte. I don't know, petabyte, yeah. So this is 48 means 12, 256 terabytes of addressable space, right? So my Pentium chip can address in my virtual memory 256 terabytes of virtual memory, but my computer has only 8 gigabytes of data. That means that I have 2 to the 33, right? 2 to the 33. So what does this mean? It means that my memory management unit should take 48 bits in, and it should put out 33 bits. So let's calculate the number of pages. So for this one, I need to know the page size. Let's say my page size on this computer is, let's say it is 1 megabyte. Okay, 1 megabyte, that means that 20 bits. It's not 4 kilobytes, but 1 megabyte. Okay, if it is 1 megabyte, then that means that my virtual addresses are like V and O is 20 bits here and 18 bits there, right? I need to make this translation to 32, 20 bits there and 13 bits there, right? So I need to make this translation from 18 bits to 13 bits. From 18 bits to 13 bits, I need to have a translation page table of size 2 to the 18. 2 to the 18 means that 256 kilowords of data. That's too large to be fitted in my memory management unit. I don't have that kind of size in my memory management unit. This picture was good enough. This picture said that I have only 16 entries, but this one says that I need 256,000, more than that, okay, registers, and I don't have that kind of register in my CPU, in my memory. So I need to find a solution for this one. So Kamil, your question comes to this. We will need to find an answer to this question, and we will find it, okay? In 1960s, people were smart and they found solutions for that one, and they found more than one solution, and we are still using them. Okay, any other questions? So it looks like I am doing this whole class with Kamil and Ahmet. Hussein came in a few times. Okay, Yusuf said once. Okay. Ilhan, are you there? Ilhan, could you make
Yes, I am here.
Okay, Ilhan, could you make a note of who asked questions? Okay, let's
Okay.
let's make a note. Maybe we will give them some Corona points. Yeah, let's give them some virtual Corona points, and later we will set up a virtual to real point translation table, Corona table.
Okay.
And
also in this class, Edis also make some points. Edis.
you like to make a point?
Yeah, he asked some questions because.
Okay. Yeah, sure. Yeah, let's take a note. I mean, of course, I
Uh-huh.
mean, Kamil said many things, and also I don't know what was the name of the person? Mustafa. Yeah, Mustafa has some problems with my voice, and that means that he asked the question. That's a good thing. So let's make a note of those.
Okay.
So out of 60 people, I am talking to like maybe five. Okay. Well, it is better than zero, right? Yeah, right. Other people, other instructors are complaining. Nobody's asking a question. Okay, if this is clear, let me move on. Let's go back to the structure of the table. Okay, this table, as it seems, it is not as simple as this. Okay, we said that in this one. We said that in an entry, we have the physical frame address and the present absent bit. It is not as simple as this. It has many information in it. One of them is the physical page frame number. We already have it. Present absent bit. We already have it. Other things, for example, protection. What is the protection for this page? My read-write protection. Okay, my read protection, write protection, execution protection. Okay, read means that it is readable frame. Write means that writable. X means that it is executable. Okay, so I can make this kind of protection information available in my physical table page entry. So for this picture, I have only two fields: present, absent, and physical page frame address. But I need more than that. I need all this information. The other one is modified bit. This modified bit is at the beginning, it is 0 along with the reference bit. Okay. If I modify any byte in this page frame, I say that this is now 1. It is not 0 anymore. It is 1. Okay. If I read any number, any address from this page, it is now 1. Okay, so reference means that. Okay, reference means that. Can I explain this? No. Well, okay. Remember, it's doing the same thing again. It's just maybe I should find some other PDF annotation tools. This is just getting too stupid. It means that if I modify something in that page, pointed by that page frame number, then I make that bit 1. Otherwise it is 0. And reference bit is the same thing too. Okay, so who makes this modified bit 0 or 1? This modified bit 0 or 1, who makes it? What did I say at the beginning when I load the page? These are both 0. Who makes them 1? MMU, exactly. Okay, no, Hussein, it is not CPU. It is not CPU. Okay, for those of you, okay, who say that there is a synchronization problem, I don't know what to do. Okay, this is what they tell me to use as a program. This is what I am using, and some of you are having it, some of you don't. I don't know why it is happening, but for you, I am recording this lecture in my OBS recorder and I'm uploading them on YouTube. Did you see my YouTube uploads, Arif? Arif, did you see my YouTube uploads? In my YouTube uploads, there is no synchronization problem. Just watch my YouTube uploads, okay? So Hussein, it is not CPU because CPU doesn't know about this table actually. Okay? CPU says that it is my 16 bits of virtual address and I need to access this memory address. Okay? I need to access this memory address. That's what I need. And if it is the task of the memory management unit to make this translation. Okay, if the memory management unit says that, okay, I will, when I say load to my register A, this address 7511, okay, if I need to load it, then that means that whatever page that I get from this one is now referenced. Somebody has read it. How about this one? Store A to this address 75112. Okay. So in this case, that means that this address is modified. Now the modified bit for this page, whatever it is, will be 1. Okay, so it is the MMU. CPU doesn't know that page is happening. Okay, my processes don't know about that. Okay, so Ahmet Yasir has another question. Do we use modified bit to determine if we need to write the data? Yeah, exactly. That's what I was going to ask. Why do we need to have this modified bit? Because I need the modified bit. If I make a page replacement, I need a page replacement. I need some memory, but memory is not available. So I need to replace one of the pages. Should I just, let's go to this picture again. If I am making this page replacement, should I just erase this page from the memory, or should I write it to the disk first and load the new one? If the page is modified, then I need to write it back. If the page is modified, I need to write it back. If the page is not modified, it is just read, then I don't need to write it back. So that modification is just for keeping information about the modified pages. How about reference? Why do I need the reference bit? Why do I need the reference bit? Modified, I understand. Should I write it back or should I just erase it? Why do I need the reference bit? It is 0 or 1. Nida says that to keep track of the page usage. Exactly. If the page is used, if the page is referenced, then its value will be 1. And I know that somebody is using it. Okay. If somebody is using it, then maybe I should not replace it. Yeah. But the thing is this. If the reference bit is 0, then how come I load it to my memory then? I mean, somebody needed it and I loaded it, right? I mean, if I am not referencing it, why am I loading it? So we will come to these kind of points later. And another one is caching disabled. I don't want this page to be cached, maybe. And there might be some other fields in my page table. So the more information that I put into this page table entry, better for me in terms of running more efficient page replacement algorithms. So most of these are for page replacement algorithms and protection, etc. But this is an expensive place because this is part of the CPU. I cannot keep very large amounts of information in this position. It looks like I am out of time. I think I need to stop at this point. Who sets the caching disabled bit? Of course, it is the operating system. Operating system says that for this page, I don't need any caching. Don't cache this page. Maybe it is part of the input-output space, address space. Maybe it is part of the, for example, shared memory. If you share memory between two processors, maybe you shouldn't cache that memory position. Because if you cache it, one of the CPUs will access it, the other one will not access it. It's like this. CPU 1 and CPU 2. Each one has its own cache. This is cache. And this is cache. If I keep that information in this cache, CPU 1 will think that it is in the memory, right? This is memory. And it will access the wrong place. So some of the pages should not be kept in the cache. It should be in the memory all the time. So operating system knows that that place is a shared memory and it has to be kept in the memory all the time. Okay, that's enough for today then. Tomorrow we will continue our discussion of the virtual memory. And we will go faster than this, I hope. Again, tomorrow I will try to do a 3-hour lecture. 3-hour lecture tomorrow. Okay, see you tomorrow.